Have you ever gazed up at the night sky and wondered about the life of a star? Our universe, a vast cosmic tapestry, is dotted with these celestial bodies, each one carrying a story of cosmic proportions. Their stories might seem far removed from our own, but stars like us have a life cycle. Imagine the birth of a star, a process that begins in the dense, dusty corners of a nebula. Over millions of years, gravity pulls this cosmic dust and gas together, forming a glowing protostar. Then comes the main sequence, the longest stage in a star's life, where hydrogen fuses into helium, releasing energy that lights up the cosmos. This state of equilibrium can last billions of years. Finally, the star meets its explosive end in a supernova. The energy released during this final stage scatters the star's outer layers, seeding the universe with the raw materials for new stars, planets, and possibly life. Just like us, stars go through a life cycle. They're born, they live, and they die. But how does this happen? Every star begins its life in a nebula, a vast cloud of gas and dust. These nebulae, floating like celestial smoke in the universe, are the cradles of star formation. But how does a nebula, something so nebulous and intangible, give birth to a star, a celestial body of such radiance and energy? Well, the answer lies in the fundamental force of nature, gravity. Within the nebula, gravity begins to pull matter together, creating a denser and denser clump. As more and more material is drawn in, the clump grows, and its gravitational pull strengthens. This clump is the beginning of a new star, a protostar in its earliest stages of life. As the protostar continues to accumulate matter, it heats up. The core of the protostar becomes a crucible where temperatures reach millions of degrees. The heat and pressure are so immense that they trigger nuclear fusion, the process that powers a star. Hydrogen atoms, under extreme pressure and temperature, collide and fuse to form helium, releasing energy in the process. This energy, this light and heat, pushes outward, counteracting the inward pull of gravity. A delicate balance is struck, a stellar equilibrium. The protostar has now reached the main sequence of its life cycle. It's no longer a baby star, it's a fully fledged star, radiating energy into the cosmos. And so a star is born, lighting up the cosmos with its brilliance. Once a star is born, it enters the longest stage of its life, the main sequence. In the heart of the star, a spectacular dance of particles commences. This dance, the process of hydrogen fusion, is what enables the star to maintain its stability. Picture two hydrogen atoms, initially separate, coming together under extreme pressure and temperature to form helium. This process is not merely about atomic transformation. It is a grand release of energy that illuminates the cosmos, causing the star to shine with a brilliance that can span light years. Every star, whether it's a dim dwarf or a radiant giant, is a furnace fueled by hydrogen fusion. The energy generated by this fusion counterbalances the star's gravity, preventing it from collapsing under its own weight. This delicate balance, this cosmic ballet, is what sustains the star throughout the main sequence. Now, you might find yourself wondering, are all stars during the main sequence the same? The answer is a resounding no. The size, color, and temperature of a star during the main sequence are determined by its initial mass. The larger the mass, the hotter and bluer the star. Conversely, stars with smaller masses are cooler and redder. The size of the star also affects its lifespan on the main sequence. Larger stars, despite their greater fuel supply, burn through it at a faster rate, leading to shorter lives. Smaller stars, on the other hand, burn their fuel more slowly and can remain on the main sequence for billions of years. So the main sequence is a time of relative stability for a star, a period where it shines brightly, powered by the fusion of hydrogen into helium. But like all good things, the main sequence doesn't last forever. As the star exhausts its hydrogen fuel, it begins to change, marking the end of the main sequence. The main sequence is a period of stability, but it doesn't last forever. Eventually, the star runs out of hydrogen fuel. When a star exhausts its nuclear fuel, it faces an explosive demise. This is the grand finale of a celestial performance that has been billions of years in the making. The star, once a beacon of light and energy, begins to feel the weight of its own gravity. With no nuclear fuel left to counteract this force, the star begins to collapse inward. Imagine this process as a cosmic ballet. The star, once so expansive and full of life, is now shrinking, folding into itself. This gravitational collapse triggers a dramatic increase in pressure and temperature at the core. The temperature rises to unimaginable heights, reaching millions of degrees. The pressure, too, becomes immense, unlike anything we can comprehend on Earth. In these extreme conditions, a final explosive round of nuclear fusion is ignited. The star, in its death throes, begins to shine brighter than ever before. This is the moment when a star transforms into a supernova, an explosion so bright and powerful that it can outshine an entire galaxy for a brief period. This supernova is not just an end, but also a beginning. The explosive force blows the outer layers of the star apart, scattering them across the cosmos. This stellar material, enriched with elements like carbon, nitrogen, and oxygen, travels through space, eventually mingling with other clouds of gas and dust. These are the building blocks of new stars, new planets, and possibly new life. The core of the original star, meanwhile, undergoes its own transformation. Depending on its mass, it can become a white dwarf, a neutron star, or even a black hole. A white dwarf is the remnant of a low or medium mass star, a dense, hot ember glowing with residual heat. A neutron star, formed from a more massive star, is even denser, cramming several suns' worth of material into a sphere only a few kilometers across. And in the case of the most massive stars, their cores collapse to a point of infinite density, creating a black hole, a region of space where not even light can escape. This is the story of a star's explosive end. It's a tale of transformation, of death leading to rebirth. It's a testament to the cyclical nature of the universe, where endings and beginnings are just two sides of the same cosmic coin. In death, a star gives life to the cosmos, spreading elements across the universe that will one day form new stars, planets, and possibly life.